Right, so let's try now to solve question number 2 in quiz 5. Question number 2 is like that. We have a collection of S-domain functions on the left-hand side, like these ones. We have 14 functions in the S-domain, and we have 14 plots of their inverse Laplace transform, and we need to pair them. But before we start, the first part of the exercise is to find the poles of these functions. But let me first tell you what the poles are of a function in general and how to find them. So when we talk about the poles of an S-domain function, which is a rational function, it is a polynomial divided by another polynomial, we mean that the poles of x are the roots of q, the roots of the denominator of this function. This is the solutions of equation q of s is equal to 0. For example, if you take here the first function, x of s is 1 over s plus 1 squared plus 1. The denominator is s plus 1 squared plus 1. This is q. So if you have the denominator, q, is this part here. So to find the poles of x, you need to solve Now, how do you solve that? You see here we have a sum of squares. It is s plus 1 squared plus 1 squared. This is a sum of squares. And when you have s plus a squared plus b squared is 0, this has the solutions minus a plus minus bj. Or if you have it in this form, if you have s minus a squared plus b squared, this has the solutions a plus minus bj. So this equation has the solutions s equals minus 1 plus minus j. Minus 1 plus minus j are the poles of x in the first example. So let's write it down. It is minus 1 plus minus j, and we can note two things here. The first is that we have a real part which is negative, which means that the inverse Laplace transform of this term here converges to 0. So this is negative, and it has a non-zero imaginary part. So it means there are some oscillations. And the third thing to note here is that because of, you can check in the lecture notes, because of theorem 417, there are several things we can tell here just by looking at it. By theorem 417, you can see that this is pretty much like the Laplace transform of sine of t, only it has a plus 1 here. It is in fact the Laplace transform of sine evaluated at s plus 1. Instead of s, we have s plus 1. Recall, let me write it here for you, recall that the Laplace transform of sine is 1 over s squared plus 1. And this is 1 over s plus 1 squared plus 1. So these two things look alike. We conclude, based on theorem 417, that this is the Laplace transform of a sine times an exponential function. So we have the Laplace transform of a sine function times an exponential with a negative exponent. Do you see anything like that here? Well, That is a potential candidate, so we can write here 1 with a question mark, and that is another potential candidate. So here we have a behavior which is oscillatory and goes to 0, and this is another behavior which is oscillatory and goes to 0. Both of these plots can potentially be associated with number 1. We cannot tell yet, but this is how we will approach these questions. Now let's move on to number 2. What are the poles here? S squared plus 1 equals 0 has the solutions plus minus j. So this is a purely oscillatory behavior, but that one is a no-brainer because the inverse Laplace of that is very clear, that this is the cosine of t. Do you see the cosine of t anywhere here? Well, that is the cosine of t, so it could be that. Let's put a question mark here. This could be 2. Do you see any other functions that look like the cosine? No? No other functions look like the cosine, so we can tell for sure that this can be associated with number 2. So this function here has this inverse Laplace transform, which is cosine of t. The third one, what are the poles of this third function? They are, according to the rule we introduced here, look, when you have s plus a squared plus b squared equals 0, then this equation has the roots minus a plus minus bj. Or when you have s minus a squared plus b squared, this gives a plus minus bj. I will prove that at the end of the exercise. Take it for granted now, but I will show you how you can derive this equation here, this property. So this is number 2. Number 2 is that. Here we have 1/10, the real part, plus minus, isn't that 1 squared? So it is plus minus 1 times j, 1/10 plus minus j. You can find more information about all these things. Check out handout 10. Handout 10. Now we have a positive. See here we have a positive real part. This means that the inverse Laplace transform of x of s grows unbounded. And another thing we can note is that again we have an imaginary part which is not 0. This means that we have some sort of oscillatory behavior. So we know two things about the inverse Laplace transform of number 3. We know that it is oscillatory and that it grows unbounded. Are there any such candidates here? Let's have a look. Oscillatory, yes, but doesn't grow unbounded. Nothing grows unbounded here. Let's have a look at the other plots. This doesn't grow unbounded. Now these are oscillatory and grow unbounded. Both this and that can be possible candidates for number 3. So is this number 3? Or is this number 3? Let's have a closer look. Does that remind you of anything? I mean, what if we didn't have that minus 1/10 here? That would be the inverse Laplace transform of what? Of the cosine. So the inverse Laplace transform here, according to theorem 417, again, is a cosine times an exponential with a positive exponent. That's why it grows unbounded, because it has a positive exponent. What exponent? I think it's time we mentioned it. 1/10. You can check theorem 417 again. But this is the inverse Laplace transform of that. Looks like the cosine of t times the exponential of 1/10 times t. So this is what makes it grow, and this is what makes it oscillate. Now let's have a look again at these graphs here. Is it this one or this one? This looks more like a sine times an exponential of something positive times t. And this looks more like a cosine, a sine of t, like a cosine of t times the exponential of something positive times t. Because at 0, it is not equal to 0, it is equal to 1, as we see here. So this must be the plot that corresponds to number 3 over here. So that is number 3. Now number 4, we have the poles minus 1/5 plus minus j, and this is negative. So we know two things about this function. First of all, it is goes to 0. And second, it is oscillatory. So number 4 goes to 0 and is oscillatory. Now this goes to 0 and is oscillatory, so this can be number 4 perhaps, can be also number 1. This is oscillatory and goes to 0, so can this be number 4? And this is oscillatory and goes to 0, can this be number 4? Let's have a look at number 4 again. Doesn't this look like, as we said before, doesn't this look like, was it not for 1/5, that would be the Laplace transform of a cosine function? So that would be a cosine of t times an exponential of something negative times t, in particular minus 1/5 times t. This is what makes it go to 0, and this is what makes it oscillate. Now, does that look like a cosine times an exponential? No, because at 0 it is 0. This looks more like a sine times an exponential. So that is not 4. It's impossible. Does that look like a cosine? No. Again, at 0 it's 0. So no. What about that one? That is a potential candidate. Are there any other functions that look like a sine that is a sine times an exponential? This is not. This is like an exponential without oscillations. This is constant. This grows unbounded, grows unbounded. This is not a sine times an exponential because it goes up and then down. This is something different. That's an exponential, and this is a little peculiar. It starts being 0 in the beginning up to time 5. This is something different. So apparently, this is the right answer. So this is number 4. Number 5. Number 5. We have, what are the poles? Plus minus j. Very good. So it is oscillatory. It doesn't have a real part, so it is neither. Oops, you weren't able to see it down there. So now number 5. This is oscillatory because of plus minus j. The poles are plus minus j. And it performs sustained oscillations in the sense that it doesn't go to 0, neither does it explode to infinity. So it can be any of these. But the distinctive feature, what makes this absolutely different from any other functions on our list, is that exponential here. What does it mean to have an exponential in your function? It means that you have a delay. You have a delay, which means this is clearly, number 5 is clearly this one. It exhibits a delay. Delay up to time 5. Where is 5 in our function? It is here, exponential of minus 5 times s. So this is number 5, and this is your delay, and after the delay it starts to evolve like a sine. So it is the sine of t. The frequency here is sine of 1 times t, 1 because of 1 times j. The imaginary part determines the frequency of oscillation. That's number 5, and that's it. Now number 6 is very easy. It's a very simple function. It is 1 over s plus 1. It's number 6, 1 over s plus 1. Here, what are the poles? The poles are just minus 1, which is a negative real number. So we know that this goes to 0. We know that we have no oscillations here. It goes to 0, we have no oscillations. And there is only one function that looks like that, which is this one. So number 7 is this one. That's number 7. Now let's move from the right hand side to the left hand side. This is x of t is equal to 1. Let's take that. It looks very simple. What is the inverse Laplace transform of the constant function 1 for all positive times? We know very well that this is 1 over s. Where do you see 1 over s here? It is here. It is. So this is number 12. So this is number 12, 1 over s. 1 over s has a single pole at 0. 1 over s has the pole 0, and that's it. What about, are there any other extremely easy functions on the right hand side? There is this one. If you notice here, this is just a line that runs through 0, 0 and 10, 10. So it is the line x of t is equal to t. It has a slope equal to 1. And what is the inverse Laplace transform of t? The inverse Laplace transform of t is 1 over s squared, which we have over here, 1 over s squared. So this is number 10. Number 10 goes here. Okay. And what are the poles of number 10? They are 0 and 0. So you either have to write 0, 0, or you can write 0 with multiplicity 2. Okay, so this is number 10. Now, let's move on to number 8, function number 8. 1 over s squared plus 1, which by the way looks very similar to number 9, which is 2 over s squared plus 1. So number 9 is 2 times the function in number 8. And what are the poles here? Plus minus j. And what are the poles here? Plus minus j. But not only do we know the poles here, we actually know the inverse Laplace transform, because that's a very easy one. What is the inverse Laplace transform of 1 over s squared plus 1? We know very well that this is equal to sine of t. And what about that? That is nothing but 2 times sine of t, and it's not difficult to tell that number 8 is here. Oscillations, sinusoidal function of amplitude 1, and number 9 is here. It's very similar to number 8, but the amplitude is equal to 2. Okay. So we have found these two. We have associated number 10 here. What about number 11? Number 11 is 1 over 5s minus 1. So the poles here are the solutions of 5s minus 1 equals 0. Equivalently, 5s is equal to 1. Equivalently, s is, I will write it like plus 1/5 to point out to the fact that this is positive. So we have a positive real pole. We have a 0 imaginary part. We don't have a j here, so we have no oscillations. And the fact that the pole is positive means that the inverse Laplace transform grows unbounded. And 11 is clearly this one over here. There is no other function that looks like 11. Now we have associated 12 with this plot here, so this is done. Number 13 now. Number 13, 1 over s minus 1/10 squared plus 1. Again, needless to say, this looks like the Laplace transform of a sine, but we have the difference is that we have minus 1/10 here. But let's write down the poles. These are 1/10. You can also write 0.1 if you like. So 1/10 plus minus j. So we have a positive real part and some imaginary part. So we know two things here. First, it grows unbounded. I'm sorry, you weren't able to see it. It grows unbounded. My equipment here at home is not optimal, but that's the best we can do now during the coronavirus crisis. At least I'm using my mobile phone, which I have attached to a very funny contraption on top of my desk so that I can record these videos. Anyway, so this grows unbounded and it is also oscillatory. In fact, to be more precise, although we don't need to here, this inverse Laplace transform looks something like sine of t times the exponential of 1/10 times t. And where do we see that? This is here. So this is number 13. The only one we haven't found is this one, which apparently must be associated with, no, we haven't found a few more. We'll get back to these ones. So let's proceed. Let's do that last one now. So it is s plus 1/10 squared plus 1 we have in the denominator, so we have the poles minus 1/10 plus minus j, but don't forget about this square. Okay, be careful with this square. This means that the poles we have inside here have a multiplicity of 2, so with multiplicity 2. So it is minus 1/10 plus minus j, and again minus 1/10 plus minus j. And this is what 14 is associated with. Now you might ask why. A few things about that particular function. First of all, because of minus 1/10 it goes to 0. Second, because of plus minus j, it is oscillatory. But what really makes it special is that it both looks like a sine in a way, but also the slope at 0, the derivative at 0, is 0. So the third element that we can take into account here to associate 14 with that graph is that x dot at 0 plus is 0. Why? How do we know? We know this from the initial value theorem. And you can do this by yourselves as an exercise. Show that the initial slope of x dot, the initial slope x dot at time 0, that corresponds to this Laplace transform, is equal to 0. You don't need to determine the inverse Laplace transform, you just can use the initial value theorem. So we have determined all functions here on the right hand side. It remains to tell this one from this one, and possible candidates here are number 1 is a possible candidate, and number 7 is another one. So is this 1 or 7? And this is this 1 or 7? 1 and 7 look similar to one another. So this has 1 here and this has 0.2. So the poles of number 1 are here, -1, -1 plus minus j. Whereas the poles of number 7 are here, -0.2. Now the more we move to the left, meaning the more the real part becomes negative, the faster the inverse Laplace transform tends to go towards 0. The faster it converges, the higher the damping. And the more we go, so as we go left, we have a higher damping. And as we move up and down, as these imaginary parts increase in absolute value, the higher the frequency of oscillations. So what is what? This has number one has a real part of -1. Number 7 has a real part of -0.2. This means that the damping of number 1 is stronger. So this must be number 1. Stronger damping. This converges to 0 slower. So this must be number 7. And these are the answers. 8, 9, 2, 10, 7, 1, 4. And then, sorry, I should have written here 6 instead of 7. 6, 1 over s plus 1. 12, 13, 3, 14, 11, and 5. Now, I promised you earlier that I would explain this formula over here. So let's do it. Why is it that this equation, s plus a squared plus b squared, why is it that this equation has the solutions minus a plus minus bj? There are two ways to see that. The first way, the more based on complex numbers, goes like that. This is a sum of squares. We don't feel very confident with sums of squares, but we know something about differences of squares. Don't we know that x squared minus y squared is x minus y, x plus y? Now, can we apply this property here, where we have a sum of squares instead of a difference? In other words, can we turn the sum of squares into a difference of squares? We can do that using this little trick. So instead of plus b squared, we will write minus bj squared, where j squared is -1, and with minus becomes plus. Now, equivalently, this is a difference of squares. So it's the first minus the second times the first plus the second is equal to 0. So a product is equal to 0 means that either the first one is equal to 0 or the other one is equal to 0. And this is one way to show that the solutions of this equation are minus a plus minus bj. S is equal to minus a plus minus bj. There is another way to show that. We can just move that on the other side. We can now take the square root on both sides. So to write it properly, this means that square root of that is, now let's write it, the square root of that is the square root of minus b squared. Now what is the square root? What is the square root of a square? We have to be careful here. Can you see it there? Yeah. What is the square root of the square of a number? Let me write it, put it in a box here. That is the absolute value of x. And what is the square root of a negative number? It is bj, from where we see that s plus a is equal to bj, or minus s minus a is equal to bj. And the first equation becomes s is minus a plus bj, and the second one becomes, let's multiply here everything by minus 1, so this becomes plus, this becomes plus, and this becomes minus. And this is a second way to arrive at the same conclusion. So let's write it down once again. Minus a plus minus bj. Thank you very much for watching, and goodbye.